we can start now. We want to continue in this room with the spread foundations. That means with clause 5. And as I see, the last person just left, almost the last. So here, spread foundations, retaining wall or retaining structures in the other room. All right.
Last person is us here.
Yeah.
We remain.
All right. So there are a few people remain. No, that's. So welcome to the session on spread foundations on clause 5 of Eurocode 7 part 3. So welcome from my side. My name is Kerstin Lesny. I'm from Germany, University of Siegen, and I was involved in TGD2, which was not only responsible for the piled foundations but also for the spread foundations. And in advance, thanks to all people who were involved in then bringing the draft provided by the PTs to the end as we have it now here. And part 3 is now under formal vote, and hopefully it will be approved in October, November, so that we can work with what you will see here, also not only for the spread foundations but also for the other foundations. We have a couple of presentations here in this session. I will first give an introduction into clause 5, and then we have a presentation on from TGB2, from Vetold, on one of those design examples on spread foundations. Then we should have another one by Fanny Deckner from TGB1, but unfortunately Fanny is ill. She couldn't come to Paris today, so good luck and all the best from our side. But luckily Gunilla will take over, and she will not only present the benchmark results but also the example provided by Fanny. So we will have time for questions after each presentation, I think, and maybe at the end we also have a couple of minutes to have a more generic discussion on clause 5. So I may start now with the general overview. So we concentrate now on the part 3, on this clause 5, spread foundations. And as you heard in the previous talks by Gunilla and Loretta, there's a whole very simple or clear structure of all the parts and clauses in part 3. With a lot of references, not only to EN 1990, but also to part 1 and part 2. But in general, as you can see here, also the clause 5, as all the other clauses in part 3, follow a certain structure, and they reflect the general contents that you have in part 1, with all the different contents here you find on the right side again. So you can work through this structure, and you know exactly if you want to know something about, let's say, geotechnical analysis, you always have to look in subclause 5 here, for example. And this is the same also for retaining structures, for piled foundations, etc. EN 1990 provides a kind of an overall framework of everything, because it establishes the reliability concept of the codes. But of course we have to use the part 2 regarding the derived values for the ground properties, and there's always also a cross-reference to part 1 as well in regard to this general design principles. Now clause 5 deals with spread foundations. That means the regular type of foundations that we know, pad, drift and raft foundations, but it is also applicable to unreinforced working platforms. An example by Fanny provides something like that, also an example on such kind of platforms. It is also applicable for structures that behave as spread foundations, like deep foundation types of structures like caissons, for example. And there are multiple cross-references between different other clauses, for example, from clause 7, 9, 10, 11 and 12 for gravity wall type structures. And there's cross-reference from clause 5 to clause 4 in regard to overall stability. Now the basis of design is provided in subclause 2, so 5.2. There's reference made to part 1, but other than that, it is stated that certain design situations for spread foundations need to be considered, including special situations as the one mentioned here. For example, foundations on slopes or on soluble, collapsible or expansive soils, special features of rock, because now the code also considers rock specifically or explicitly, or in this case here also potential scour, which may cause failure of a spread foundation. There's something said about the selection of geometrical properties, including setting out tolerances and working space, and provisions are given on permanent and variable actions, what type of actions need to be considered or which may be relevant for spread foundations, as well as cyclic and dynamic actions if they are relevant for your design. There's also a consideration of environmental influences. In the case of spread foundations, it is a specifically frost impact that needs to be considered. Another issue which has an impact on the quality of the design and is related to the geotechnical categories, which we heard about earlier this morning, is that the zone of influence need to be considered for the specific type of structure, in this case the spread foundation. So the spread foundation has a zone of influence beneath the foundation base, where it transforms the stresses from the structure to the soil. And this needs to be considered in regard to the minimum depth of the ground investigations, whereas the type of investigations and also the number of investigation locations is established according to Part 2. The depth of the minimum depth of the investigations is specified in Part 3 for the relevant structures. So here for the spread foundation in subclass 2, and here in table 5.1 you can see the minimum depth, and it depends on the type of the spread foundation and its load transfer zone, let's say. Now 5.3 includes some provisions on the materials. So regarding the ground materials and the properties, there's a reference made to Part 2. But there's clearly stated that you may either use total or effective stress analysis depending on the type of problem that you have, considering the ground permeability, potential failure mechanisms, and the type and duration of loading. And for that you need to choose the appropriate total or effective stress properties. There's also mentioned the type of the material of the footing itself, let's say plain or reinforced concrete, and it is stated that these materials should comply with relevant material standards. Compared to the existing code, the current version, there's also an explicit guidance on the groundwater in each chapter, and here we have it in subclause 5.4, where reference is made to Part 1 regarding the definition of representative groundwater conditions. That means groundwater levels, for example, and pressures. It is stated here that you should consider those levels and pressures as long as they affect the limit states of the spread foundations, of course. And also maybe some rare situation which are not always typical, but they can occur. For example, if you have a groundwater level which is close to the foundation, that you also consider the effect of pore water suction, so a negative pore pressure, not only a positive one. And there's a reference also to clause 13 in regard to groundwater control measures, and this is also something which is in each of the other clauses as well. As shown before, the geotechnical analysis is then presented, let's say, in subclause 5.4 and 5. And here you can see diagram on the different limit states of the spread foundation. This is nothing new, of course. So we have to consider the ultimate and the serviceability limit state. And for the ULS, we, for example, consider bearing failure, sliding failure, and a kind of rotational failure. What is new is that explicitly you should consider the structural failure due to excessive foundation movements, which may produce an ULS situation of your structure and the spread foundation. In the serviceability limit state, you have to consider settlement, heave, rotation, tilting, etc. Now regarding the rotational failure, we consider two different types of rotational failure, depending if a failure of the ground is involved or not. So here on the left side you can see a situation where there's no failure of the ground involved, so you have a pure rotation ideally around the front corner of the foundation, and this is called toppling. This is only kind of a stability issue, let's say, so you verify the static equilibrium, and this is to be done according to EN 1990, so this is not regulated in EN 1997. But what is regulated there is the second type of failure, where you have a kind of a rotational bearing resistance failure, where maybe the soil moves here in this direction but is concentrated more or less below the front edge of the footing, and this is called overturning, and this needs to be verified together with the bearing resistance proof. So this is one proof, let's say. Now the geotechnical limit state analysis considers the calculation methods for bearing and sliding resistance, which are provided now in the main text. This is also a difference to the existing or current version of the code, where you have everything in the informative annex. But here we could reach a certain harmonization because everyone normally uses the well-known Taskgroups bearing capacity equation. So this has been now put into the main text for soils and fills, but there's also additional information on bearing resistance on rock mass and also on empirical models, because in some of the countries those methods are quite being used frequently. And there's also guidance on verification of prescriptive rules, testing, and the observational methods, which are the other types to evaluate limit states other than the partial factor method. Now you can see some screenshots out of the code text. I don't want to present everything, that's a little bit boring, but just to have some important aspects here, which are then highlighted a little bit. Here we have the bearing resistance on soil and fill, and there's a distinguish between the undrained and the drained case. And you can see here we have the well-known bearing capacity equation, whereas always all parameters are defined in the Annex B4. So there does exist an Annex B, which includes calculation models for clause 5 spread foundations, and which is quite extensive now. We have another calculation model in Annex B.5, which deals with punching. That means bearing resistance on ground underlain by a weaker layer. Here you see the provisions on rock mass. It is distinguished if the rock mass behaves as a discontinuous medium or a continuous medium. And for the latter one, we have another calculation model in Annex B16, bearing resistance on rock mass based on wedge equilibrium. Here you can see the bearing resistance from empirical models. It is stated that it should be verified that they are suitable. And we have another calculation model here in Annex B6 with the bearing resistance from Minar pressure meter tests. Also, and the sliding resistance, so everything before dealt with the bearing resistance, with the sliding resistance. We have again the differentiation between the undrained and the drained resistance. But this is, let's say, nothing new from the methodology. Also, as the bearing resistance calculation, this is what you know already. So just, let's say, from the presentation here in the code, maybe it looks a little bit different from the first view, but in the end, the way to calculate it, the bearing resistance is more or less the same, but you have more clear regulations on how to do that. Let's go over to the serviceability limit states. Here it is clearly distinguished between settlement and heave. Also, settlements caused by consolidation and creep are considered. And for the serviceability limit state, there's also a lot of additional calculation models provided in the annex. For example, settlements caused by consolidation, the time settlement behavior, or also settlement evaluation based on field test results like pressure meter test as well, and also CPT results. Further aspects are also dealt there, for example, guidance on bearing pressures for structural analysis, and there are some additional calculation models in Annex B on the definitions of the stiffness values for subgrade modulus calculation models, let's say. So overall, you can see there were a lot of additional calculation models in the Annex, 16 different annexes you have in the Annex B. Now, let's go back to the main text where the ultimate limit states the verification procedure is dealt with in subclause 5.6. And because I focus now on the part 3, I do not elaborate what is written in EN 1990 so much. As stated before, you have to work with 3 different codes, or maybe with 4. So we have EN 1990, you have all the 3 parts of EN 1997. So here, regarding the partial factors, you have to establish verification cases in regard to the actions or the effect of actions, which are defined in EN 1990, which will be combined with either the material factor or the resistance factor approach, which is regulated in EN 1997. And this ends up in 5 possible combinations of partial factors. But just to say it from the very beginning, that doesn't mean that you have to calculate all 5 calculations. So usually you decide for 1 or maximum 2, depending also what will be then later on defined in your national annex. There are also combination factors which are defined for multiple variable actions in EN 1990 as well. So if you establish the load combinations, you have to work very much with EN 1990 as well here in this regard. On the resistance sides, we have the partial factors in part 1 for the material factor approach and in part 3 for the resistance factor approach. And these partial factors are established for the consequence class 2 for permanent and transient design situations, but they are all NDP, so they might be adjusted by your national annex. And there is a possibility to reduce for transient situations those factors as long as they remain larger than 1. And this is something, for example, what we have in Germany, where we calculate with smaller partial factors temporary design situations, like for example a construction pit, so retaining structures for a construction pit. Now let's go over to the verification. For overall stability, there's reference made to clause 4. For bearing resistance failure, we have here the limit state function, not in the probabilistic way as this morning, but here on the regular partial factor method approach, with the design value of the normal force in the footing base compared to the normal resistance in the footing base. Here you have to consider that in case of combined loading, you have a load inclination, which needs to be considered with design values of the horizontal and the normal loads. And for the design eccentricity as well, you have to use the design load components, so the actions. In regard to the design eccentricity, because now the overturning failure mode is also considered here with the bearing resistance, you have to think a little bit about the eccentricity. So if it's extremely large, it is a little bit hard to assess when is it large, but you have at least to consider that. You should consider if you can apply the regular bearing capacity equation, because it has been established for a moderate eccentricity, and those concept with the effective width of the footing is not suitable for large eccentricities. So in this case, you may use numerical methods instead, like FEM analysis or something like that. And another issue is that depending on the verification case that you have, that means the way that you combine partial factors, you have to consider if the normal force in the footing base acts favorable or unfavorable. Because here, for example, you should use the design actions. And so if you are not sure how it acts in the limit state verification at the end, you have to consider 2 possible calculations. One, where the normal force is treated favorable, and second, where the normal force is treated unfavorable. But you should not mix. So in one calculation, it's always either favorable or unfavorable. So remain consistently in one calculation then. Regarding the sliding resistance and the ultimate limit state verification, we have this limit state function here. The horizontal load, its design value, let's say the resultant horizontal force in the footing base. Then we compare it with the resultant frictional resistance in the footing base and the resultant earth pressure at the front of the footing, always the design values of those. And here we can need to consider, for example, that those two resistance components shall be related to the scale of movement anticipated under the limit state. Here, design loading, and you should consider that they may be mobilized at different displacements of the footing. For the earth pressure here, you should make sure that it exists over the lifetime of the structure and should not be removed in between, let's say. And we have a specific requirement, for example, on undrained sliding resistance, where you should make sure that the resistance in the base, in the undrained case, should not exceed this value here, 0.4 of the representative normal force. And this should be to prevent that simultaneously bearing resistance failure occurs in case that there's limited contact of the footing base with the ground. So this is an extra verification that you have to do here. Now, in the end, for the ULS, have a short look again on the partial factors, and I'll summarize them here in this table, just to show that you have to work with the different codes. And again, here the actions and effect of actions are defined with the verification cases in EN 1990, and this provides you with the different partial factors depending on the different verification cases. Then for the ground properties, the partial factors are defined in part 1 of EN 1997. These are these two lines here. And for the ground resistances, there we have the table 5.2 in part 3, clause 5, where we have these values here. And these are the 5 possible combinations I mentioned earlier, but usually you decide for one or the other, either if you use material factor approach or resistance factor approach, depending on your national traditions, let's say, and what is defined finally in the National Annexes. So here in the MFA, either A and B or C, in the RFE, A, either D or E. Whereas normally it's D, but E you can use, and there's another provision here. So combination E you can use if the load inclination is small, that means not larger than 20% of the normal force in the footing base. So I have to check, but either at the end you will probably decide for one of those combinations. In the serviceability limit states, the criteria for verifying this limit state, as we heard this morning, this is very much a discussion or negotiation between the client contractor and you as the designer, but there are some criteria for orientation provided in EN 1990 Part 1, Annex A for selected structures. Otherwise, this subclause 5.7 deals with the way that you have, of course, to fulfill tolerable values of settlements, differential settlements, heave values, or something like that. And additionally, there is also provided some limits of maximum load eccentricity in the SLS, which is this table here. And this more or less should guarantee a little bit that the foundation base is mainly loaded by compression, so that you do not waste part of your foundation base for tension loading, which cannot be transferred to the ground. So this is a kind of prerequisite that is known also in other existing standards in the European Union at the moment. Further contents deal with implementation of testing, of design, testing and reporting. I only want to point out, for example, the use of plate loading tests. There's clear guidance on when they can be used for the design of spread foundations. And only if the size of the plate and the size of the footing is being considered, so that they are representative to each other. Because usually the size of the plate is small compared to the size of your footing, so only a certain reduced zone of influence is analyzed by the plate load test. So this is what you have to keep in mind. And otherwise, you should be very careful in using those type of tests for the design of spread foundations. Now, in the end, we have, I think, a more clearer and unified structure. You know exactly where you find what. It's an increased harmonization in regard to the calculation methods, and there's a lot of more calculation methods now in the annex. There's a clear distinction between soil, fill, and rock. And there's no major changes in the design methodology, at least for spread foundations. So you design it in the way you're used to, but let's say the verification procedure is different now because you have to use the different codes, and also there's a different format with the verification cases and so on. So this is what you need to get used to. All right, so this is from my side. So thank you very much for your attention.